Look at all these brave souls that made it here safely. Okay, it took me almost 2 hours to get here. Top that. Go. 2 minutes? Where do you live? Well, good for you. I take the bus, so that extends my stay. The bus does fine. That's what I like it. But Foothill doesn't do fine. So today, though, I realize it's a perfect example. Friction specifically comes a little later, but we bring it up in chapter 2. And so it'll fit right into us talking about inertia. We just started bringing it up last lecture. So today I'll finish chapter 2 and remind you that you have homework on chapters 1 and 2 due Sunday night. It's posted, it's listed as such in the schedule and calendar on WebAssign, and you can work on it and complete it or turn it in up through 11:59 p.m. Sunday night. After that, sorry. Okay. Unfortunately for you, we won't have time to expose you to all the wonderful things I like about physics, because it's only a semester class. And so I took the liberty Wednesday on National Static Electricity Day to show the Van de Graaff generator. But this is my favorite toy along with static electricity. So no, you're not being tested on this. Okay, so just relax. Anybody seen these? Yeah, they're sold as a toy. It's called the Fun Fly Stick. So if you Google Fun Fly Stick, you'll find them. They're $25-ish. They have a clear version now. Basically, all it is inside is a little Van de Graaff generator that we had Wednesday. There's a belt in here with a little motor, battery powered, obviously. And every time it comes off the belt, it separates charges, and they build up on here. It comes with these really light metallics, kind of like Christmas tinsel, but not quite. And so if I charge this up, you can hear it. This now has a little charge, and it's totally safe. That's what I didn't even feel anything. When this touches it, it'll transfer that same charge to it, and you can see it repelling. It doesn't like it. And so now, two same charges, and they repel, and you can magically levitate things. My daughter loves this. If you're into Harry Potter, you can. Help me out. Wingardium Leviosa. No, it's Leviosa, not Leviosa. Oh, I don't know, whatever it was. But it's just because there's a force, see, that's where it comes in, what we're talking about, between charges. There's forces between masses, me and the Earth. Because we have mass, we gravitationally attract each other. I gravitationally attract your mass, and you gravitationally attract my mass. Well, these charges electrostatically repel each other. There's a force between them. This one on that, and that one back on the stick. And this was enough to overcome that guy's weight. He has very little mass, but it is trying to be accelerated downward by Earth. And that's what we call weight. Mass times gravity, the acceleration due to gravity. You can write that one down, but it is in your book. That's his weight. Weight is a force. That's important. A lot of people get those confused. If you realize weight is a force, that'll help you a lot. And so there's a force down on this foil. Then how does it stay up? There must be an upward force as well. And the second half of chapter 2 talks about forces and net forces and whether something's in mechanical equilibrium or not. Vertically, work with me here, this isn't moving up or down right now, is it? So what two forces must be balanced? Upward and downward, that's right. There's two forces on it, but it's not moving vertically at the moment. I'm trying. If the electrostatic force, the upward force, is a little greater, it can move up. Or if weight's greater, it moves down. And that's what we call a net force. It's just the result of all the real forces acting on something. You can attract your hand back to your... Anyway. Whee! I see a question. Go ahead.
So with the instance with the ball where you throw it up, there's an upward force, and then there's a downward force working on it. When it pauses at that point, it's not in equilibrium, right? Because the downward force is now greater.
And I'll be more explicit. Bless you. Because that's a homework question. You looked, right? Well, you should be looking. Because most of those, I give you the answer straight out. Or the book does. And that's one of them. So if you didn't realize, let me find something to toss that's safe if I drop it. This. So, what forces are acting on this block right now? Gravity and my hand. And that's in this chapter 2. The hand, we call that a support force. Makes sense, I hope. It's also in physics called a normal force, if you hear that term. A normal force. That's normal meaning perpendicular. When an object is at rest on somewhere, the surface exerts a support force, and it's always perpendicular to that surface. Thus, if I raise this up, the normal force, the support force, is not straight up anymore. It's at a little angle, perpendicular to this surface. Does that make sense? And so, this guy's weight down, support force up, and they must be balanced right now because the net force is 0. It's in mechanical equilibrium. It's not changing its motion. This, in physics, is what we call, physicists, free body diagrams. Free body diagrams. You have an object with a certain mass, and it really does help you understand the problem. Too many people, when they go on in physics, they know how to do the math. They have all the equations, but they don't know where to start, and they're going down the wrong road. You really need to draw a picture and realize what's going on. What equation do I set up in the first place? Then it's all math. So in this case, you have a force due to its weight. And you guys might as well know that's its mass, based on how big it is, and its acceleration. We'll cover this more. Its acceleration. You saw that the first day as my example equation, F equals ma. But that's what causes weight. Specifically, this acceleration, we call g, the acceleration due to gravity. Its value is 9.8 meters per second squared. That will make more sense next chapter. But I find it useful for you guys to know now. Basically what that means is, when you take this, and if I just let go of it, it starts out not moving at all, but it's moving slowly, and it'll move 9.8 meters every second. And each additional second, it'll add 10 more meters, 9.8 meters per second. So in the first second, it gives you an idea of its acceleration. So that should make enough sense for now, what you need to know anyway. So if you want to know how somebody's weight compares to somebody's mass, this is the formula you need. Mass is measured in kilograms. That's gravity, not grams. Trying to distinguish. So the standard unit for mass is kilograms, and standard unit for acceleration is meters per second squared. So example, if I weigh 175 pounds, that's the unit we're used to. It's not a standard unit in science. We like to use newtons after Isaac Newton because he figured this stuff out. Well, we're in America and I still have a hard time remembering what I am. Let's see, I think that's roughly 70 newtons. So let's pretend I'm 70 newtons. That's the force of my weight. That's the gravitational attraction of the Earth pulling on me. What's my mass? Mass and weight are different things. Well, F equals mg. That's our relationship. That when you try to accelerate a mass, that's the force acting on it. We're going the other way. I told you the force, so let's figure out how much mass that thing has. If you divide both sides by g, you can rearrange the equation to be that. Does that make sense? Be honest. The force is 70 newtons. This is 9.8 meters per second squared. For simplicity, 70 divided by 10 is 7. So the mass is about 7 kilograms. That doesn't sound right, so I'm sure I converted wrong here. But it doesn't matter. That's not my point. I know I'm more than 7 kilograms. But anyway, that's how you would play that game. And I'd bring this up because, one, I want you to know this already. It's in the homework. And two, too many people get confused between mass and weight. They're not the same things. Example. Our weight here on Earth is due to the attraction of our mass with the Earth's mass. That's how we get this value. But that's a different value, say, on the moon. The gravitational acceleration's less, roughly a sixth less. Thus, your weight would be less on the moon, wouldn't it? Do you see that? I'm not getting any responses. If your weight is mass times the acceleration of gravity, and the acceleration of gravity is less, then your weight will be less. That's why people on the moon, it looks like they're weightless. Not weightless, but they're less weight. But your mass does not change. You still are made up of the same amount of stuff. So you have the same mass on the moon as you do here, but you weigh less. You with me? This just started me off on explaining all the stuff I wanted to. I know I haven't answered your question yet. So, if I toss this up into the air, what force is acting on the block while it's in the air? Gravity. Good. Anything else? There is some air resistance. Good. We'll neglect air resistance for now to keep things simple, because it's not much on this, so we won't complicate things for the moment. Are there any other forces? The amount of force I threw it with. What about after it leaves my hand? Does it still have a force upward on it? That's my key. On the way up, after my hand, before it gets to the top. Now, it's going up. Good observation. Its speed is decreasing. I think you said gravity's pulling it down. What's keeping it going up? It's inertia. I want to emphasize, inertia is not a force. It's just a property of matter. If we got rid of gravity and I did this, what would happen? It would keep going up, and specifically at what speed? The same speed that it left my hand with. Newton's first law, things at rest want to stay at rest, and things in motion want to stay in motion unless a force acts upon it. That's the gist. So yeah, it would stay at the same speed. When we like to say, yeah, it has inertia, it would just keep going. But there's a force down on it, slowing it down. And so it decelerates. Like when you hit the brakes on your car, that's what you can relate to. You're still moving forward, aren't you? But you're slowing down. So when you hit the brakes, the force is that way on you. But you're still moving this way. That can happen. So in the air, the only force on it is gravity. Here, at the top, and on its way down. And does that force change? No, it's gravity. It's fixed. So the whole time it's in the air, it's trying to be accelerated downward. It slows it down, stops, and then of course starts speeding it up back this way. So would you say it's in mechanical equilibrium now? Waiting for more people to commit. I've heard like 2 or 3 yeses and then 1 head nod. Yeah, what's the net force on this right now? 0. In the air, what's the net force? It's weight. It's mass times the acceleration due to gravity, 9.8. And that's the only force. We're ignoring air resistance. Good. Thus, is it in mechanical equilibrium in the air? No, absolutely not. Because it's moving. It's changing its motion. There must be a net force on it. The net force is the only force on it in this case because there's nothing to balance it. Just its weight.
Is there a split second at the top before it starts going downwards in equilibrium?
And that's a good question. Is there a split second right at the top where it's in equilibrium? What's your gut say? Yeah, and that's what most people's gut say, so you got a good gut. Your gut's wrong, though. Sorry. Because as soon as, well, actually, the whole time, gravity's always pulling it down. Now, and even at the very top. It stops its motion, but it's changing from moving that way to start moving this way. So it's still trying to change it. Thus, it's never in equilibrium because the net force is never not 0 in that case.
But then the forces of it, your motion and your force that you put into it to throw it up is then at some point equal to the force of gravity, right? Causing it to go to a type of equilibrium.
Yeah, how do these two forces compare? That's a good question. Is it equal to it? I have to exert a force initially on this to overcome its weight, right? Right now, my support force equals its weight because it's not changing its motion. To get it to change its motion, my support force must be larger than its weight to initially get it up to that speed. But as soon as I let go of it, inertia takes over. Good. Yes?
So I was thinking that when you throw the block, talking about the equations, that's assuming a vacuum, right? Because you do have air resistance for everything outside of a vacuum, right?
That's correct. We were ignoring air resistance. With air resistance, you have the force down, mg. And that's the force of its weight. This is while it's in the air. If it's moving up, then the air resistance is actually trying to push it down also. And you have a little bit of friction. On the way down, it's actually hindering it a little, and it goes this way. And so technically, yes, the net force would be the difference. The weight minus, in this case, plus the friction, because they're both down, nothing up. And in this case, like that. For that specific example, this is extremely small, and so I ignored it.
In the 1950s or 60s, how did physicists know about the resistance for the space capsule to come back to the Earth? Coming through, how it gets so hot. How would add more resistance? How would scientists know that would happen?
So how did scientists, were they able to account for spaceships re-entering the atmosphere? They had observed it by then, and Galileo and Isaac Newton had already come up with this. And basically, you knew it when you were a kid, you couldn't put it into formulas. Because when you drop a piece of paper, You can see the air resistance. We learned about air. We know it can slow things down, and they figured out exactly how much. And it depends on how much air is in it, too. Higher up, there's less air, so there's less friction, air resistance. You'd fall faster.
Oh, right.
But as you get closer to the ground,
Coming back from space, too.
yeah, that friction, conservation of energy, turns into heat. You know that. Do this and you warm your hands up. And so they had to supply enough fuel for such things and be able to dissipate that heat so they didn't burn up. See, physics and everything. Is there another question?
Equilibrium only applies to things at rest then.
That's the next stage. Does equilibrium only apply at things at rest? No. It's when, I like to think of it when there's no net force, when it's not changing its motion. So example. You get rid of friction, like we did today driving around. See, it really does go at a constant velocity if you can get rid of friction. It's blowing air out the bottom. You can see the effect of gravity because the ground isn't level. What was my point? Oh yeah. So when it's in motion, it wants to stay like that. It resists a change. Just like the block when I threw it up, forced to throw it up, but as soon as it left my hand, there was no more force from me acting on it. Inertia kept it going up. Gravity was acting on it, though. In this case, what acts on it after I push it? Friction. Very, very little now, though, because you can see it's not slowing down like we're used to, like this. So if friction isn't acting on it, it would just ideally keep going forever at that speed, right? So at least horizontally, there's no force acting on it. Do you see that? It's moving forward, but not because something's pushing it all the time. That's hard for some people to get their brains around. So we would still say it's in mechanical equilibrium because the net force on that when it's moving is zero. The net force is zero, but it's moving. Net force. Net is a result of all the combinations of forces. And in this case, we use the force to get it moving, but after that, inertia. It's just moving until something else acts on it. It's happy.
What about the upward force from the air?
Okay, now there is still gravity down and the floor supporting it. So vertically, we would say it's in mechanical equilibrium as well because its weight and the support force are equal. If they weren't equal, if this was bigger, it'd be sinking into the floor. And if the floor was pushing harder, it'd be lifting up off the floor. You feel that sensation every time you go on a roller coaster. You know, the support force and your weight aren't balanced there because you're going in a circle. That's centripetal force. But you can feel that difference. Or in an elevator, woo! Put yourself on I do this, especially when you go to the cool hotels that have the fancy elevators with 28 floors. If you can get a bathroom scale, go in the elevator. And when you first start, before you start, what's the scale read? Your weight. You're balanced. That's how it tells you your weight. It's actually the support force it's measuring. But when you're in equilibrium like that, not trying to change your motion, they're balanced. And so it equals your weight, and so that's how it works. If you start accelerating upwards with the scale, does that change my weight?
No, but the force that is,
Does it change my mass?
No?
Now what?
the support force is greater.
The support force is, yeah. Earth is still trying to accelerate me down, but it's trying to accelerate the scale and me up. I have mass, I have inertia. I don't want to move. I have more mass than the scale. I don't want to move more than the scale does. And so it's kind of like the scale gets pushed into me, and it supports me with more force than just my weight to get me moving and change my motion. And the opposite when you stop at the top, that light feeling, or when you go over a hill, your inertia wants to keep you going up. I'm moving, I'm happy now, so I'll just keep moving. But wait a minute, the elevator stopped. Gravity starts taking over, and then you come back down onto the scale. But for a while there, it doesn't have to support you as much because you're still moving up. Questions? See, I love how our discussions go. Yeah, I get an outline. I'll get it all in, but this isn't where I was having. This is good stuff. So, I wasn't specifically going to cover centripetal force this semester. Has anybody heard centripetal? Yeah, at least some people have. Or centrifugal, it's the unreal one. But you can understand it now. It's just that force when you're going in a circle. You're in your car, and you take a strong left turn. You're in the passenger side without your seatbelt, and what do you notice? You smack into the door. It feels like you're being flown outward. That's a reference frame. It's a relative force. What's really happening? Think about it. See if you can tell me.
Your inertia is going forward, and so you're wanting, and then the car then takes you this way, and your momentum wants you to keep going forward, but then whatever you're in turns, and it goes in that circular motion.
Well done. That's correct. I'll repeat it now. I'm going to face you so you don't have to see my hiney. So if you turn this way, well, I was in mechanical equilibrium. Let's say we're going 50 miles an hour. So I'm still going 50 miles an hour, but the car turned in front of me, didn't it? So what do I run into? The door. Now that puts a normal force on me, perpendicular, which will be directed to the center of the circle we're trying to turn. It's a support force that pushes me and redirects me that way. And it's constantly pushing on you. And so it feels like to you you're pushing on it, but of course when you do that it's pushing on you. We'll get to that with Newton's third law in a bit. But it's because your inertia, you're just trying to keep going straight. What if all of a sudden we could turn off gravity? What would happen to the Earth? Yeah, that's true. I didn't think of that. It would fly apart. Good point. More simplistically though, you're right. The Earth goes around the sun. It's held by the sun, right? If we got rid of that gravity even there, what would happen to it? Would it keep going around? All of a sudden, boom, you turn off gravity. It was headed this way at that moment. So it'll just keep going that way. You can do that with a ball on a string, spin it around, and when you let go of it, it actually goes straight. That's what Newton says. Go try it. Because you might notice it doesn't go straight. Why would it not go straight? Very good. Because we're still on Earth, and as soon as you actually before you let go, but gravity is going to start making it look like it's flying in a parabola. Yeah. So if we did that out in space, boom, it would go perfectly straight. You could do it on a tabletop maybe and see that it goes straight. Do you have a question, Brian, I thought?
Yeah, but like if the gravity between the sun and the earth were to disappear, the earth wouldn't be able to stay in the same place because the sun still is moving. You know, I mean, the sun's rotation and the sun's gravity wouldn't change. So I think the Earth would still stay in orbit, having a hard time understanding what you were trying to say. If
You-
gravity, if we were to eliminate the gravitational force between the Earth and the Sun. I think if gravity, the gravitational force between the Sun and the Earth were to disappear, wouldn't the Earth move towards the Sun?
So a little confusion with my gravity example between the Sun and the Earth. You're right, if we only turned off gravity on the Earth, sure, we'd still have gravity with the Sun. And I wasn't clear. We turned off all gravity, which was caused by masses. Then there would be no mutual attraction, no force between the Sun and the Earth. There would be nothing pulling them together. So like a ball on a string and you cut the string, the Earth already in motion will maintain that motion the instant the string is broke and head off at a constant speed in whatever direction it was headed at that moment. Because there's no more force trying to pull it inward into that circle. It's like you not wearing your seatbelt in the car with the door open. You turn too hard, you're going to fly right out the door and straight and keep going until gravity pulls you down and you get road burn, among other things. Okay, I want to make sure I'm not forgetting something for your homework. So the book defines it. We've explained force now, but I like to think of force as any influence, this is in your book, that tends to accelerate an object. That is essentially Newton's second law. We're not there yet, but that's why these lead into each other. By acceleration, that means changing its motion. Changing how fast it's going or not going. So a force is any influence that causes some object to change its motion. We've seen that. You know net force, you know equilibrium, you know support force, you know gravity. I think I have, but let's make it more specific. What if you're hanging, this is a pulley, and you got a rope over it. And you got to pull down over here with a certain force. How much force do you think that has to be compared to this side? Half? Why? Yeah, you know enough about pulleys that you know somehow it helps you. Yeah, you're on the right track. The specific example I drew, it's not half. Yet. I was going to do that next. So I'll tell you how you can use a pulley to do that. Pulleys just redirect the force. So in this case, what's pulling down on this guy? Gravity. So we get his weight down. Remember it's mass times the acceleration of gravity pulling it down. The string's pulling up on it. Tension. That's a force. And if it's just enough to hold it there so it's not moving, how do these two compare? Mechanical equilibrium. The net force is? So is it changing its motion? Its acceleration is? Net acceleration, is 0. Good. So it's just sitting there. Well, the tension in this rope is just redirected over here, and so this force will balance that tension. You have to apply force that is equal to this tension, which is equal to the weight. So in this case, all you have to do is just hold it with the weight of that. What happens if you pull harder than that? Yeah, then we're going to have a non-zero net force, because this will translate over here, and this will be bigger than that. And we'll get a change of motion, and this thing will start moving up. Same mass tied off to both sides. Let's draw our free body diagram now. You have the same weight. What's holding it up? Its weight's holding itself up? The tensions, right. So we have tension pulling up here, but we also have it here, don't we? So you have this tension and this tension. And now what's the net force if it's not moving? 0. That tells us this force of weight must balance the combination of these two. You with me? You have the two tension forces up and the weight down. If it's not moving, or, I don't know how, but for theoretical sake, it was moving at a constant speed. Remember, constant speed is still mechanical equilibrium because it's not accelerating. But anyway, think of it at rest. It'll probably make your life easier at this moment. Then that is 0. And you can put this on the other side. And just like I said, the weight is balancing the two tension forces. And in this case, each side of the rope only has to support half of the object's weight. And you can play with pulleys and redirect and go around multiple times and make it even less or more, depending on how you want to set it up. But these are force body diagrams and how you would do support forces. In these cases, if it's in mechanical equilibrium, all the up forces balance the down forces, or all the sideways forces to the left balance all those to the right. You with me? Does that make sense? Okay. Let's try your clickers. So I'm assuming some of you have gotten some since last time. I want to ask you some questions and see what you think, and you can test it out. Okay, I've opened polling. Oh. So today, those of you with your clicker, make sure it's on channel 40. Lame laser, sorry, the batteries are going. Bottom right, there's your channel. 44. That's for the clickers. If you have a mobile device with responseware, use that session ID to log in. I've started, so you can read this and answer A, B, or C for 1, 2, 3. A, B, or C, 1, 2, 3. What do you think? Good, it's working. Got 10 responses so far. 11! I don't mind giving you a clue at this point. It's been 2 days. Scientific claim. What makes it scientific? Do you remember what was specific about science? Don't call it science if you can't. Prove it wrong. That's a clue. If one of those you can't prove wrong, it shouldn't be a scientific claim. What do you think? Got to be able to test it. All right, and I got this nifty countdown timer, so you have 27 more seconds and we'll close polling.
Are we going to talk about energies like kinetic and potential?
Are we going to talk about energies, kinetic and potential? We will. Yeah.
Question, if there's a check, if I see a check mark on my phone, that tells me that my answer's been submitted, right?
Each phone is different, uses a different app. I'm not sure, but that sounds logical. The clickers give a smiley face. Check marks are usually good. Okay, it looks like most of you thought answer C. Which of the statements below is a scientific claim? And then the others were split on A and B. Well, only statement 1 was scientific because it can be tested. Actually, it has and been proven wrong. Human beings will never set foot on the moon. Well, we went to the moon and set foot on it, so it was proved wrong. So that means it's considered a scientific statement. Does that make sense? Now? Why? Let's see, what's it say? Statement 2 cannot be tested. I can read better. What was 2? Some of the laws that govern nature cannot be detected by scientists. Well, that might be true, but there's no way to test it because they're undetectable. Maybe you could just reword the question and turn it into a the statement. Reword the statement to make it scientific, but the way it's worded there, you can't detect it, so you can't prove it wrong. So my point is, you can't say it's a scientific claim. Make sense? And the third one, what's it say? That's speculation. It is quite possible, well, that's always a tip-off right there, that in some other galaxy, the laws of physics are fundamentally different than the laws here. Could be true, but is there any way to check for it? No. We could go to one and find out, but we don't know all the others and say we think we found them all. Well, there could still be another one that's undetectable. Point is, you can't test it.
But wouldn't the laws of physics then be the same in the whole universe? Because wouldn't the force that created our galaxy be the same?
Wouldn't the laws of physics be the same everywhere in the universe? We've made that assumption. And because thus far, everywhere we've looked, it seems to work. But we don't know that for sure yet. But it's serving our purposes really well thus far, and we have nothing else to go on. So there's a good encompassing working scientific theory. It could change, but not yet. Okay, good. Yay. It did something really weird. Well, that's all right. They were just more, the others were more of what I've already asked you, and I mainly wanted to do that. Give you guys a chance to check your clickers out, and I can now see. Any problems with the clickers? Yes?
How do you know if we participate?
Did you get a smiley face?
I got a check mark.
Or a check mark? Then you did. And I'm...
Particularly, like for our grade.
I will eventually post all these, that's for sure. And you can always email me and check. I am not counting participation points yet. This was your trial week to get your response figured out. Starting next week, whenever I use them, I will count that towards your participation points. And I will, I export them out of this clicker software, and I get them in my spreadsheet, and I'll post those eventually so you can maintain and see what you're doing. But you can pretty much trust, if you got a check mark or smiley face, and I asked one question, you got all the participation points today. And again, it doesn't matter if you're wrong, only if you participate. 4 minutes, I can do it. One more thing. If I pull this block with a force of 100 newtons, and it's in mechanical equilibrium, which means what? Constant speed, not accelerating, not changing its motion, and what?
Net force is 0.
Net force is 0. Good. I don't mean to say that. Good. So if I pull it with that, is there any other force acting on it in real life? What? Friction. Which direction do you think? Opposite, yeah. Of friction. Do we know what this value is? We can compare it to this. Do you think it's more, equal, or less? If you think it's more, raise your hand. Equal? Few of you. Yes. Equal? Less. The rest of you don't know. Take a stab. If it's at mechanical equilibrium, then the net force must be 0. There's no net acceleration. There's no net change in motion. It's moving forward. Let's get something you can relate. You're in your car and you're going 50 miles an hour. No, we'll be realistic. You're going 80 miles an hour. It's Utah, right? Okay, if you're maintaining 80 miles an hour, do you see that you're not accelerating? The net force on you is 0 then, because you're not changing your motion. You're happy going 80. You're not going faster this way and you're not slowing down. Thus, that hopefully now will tell you that all the forces acting on you must be balanced. The force propelling you forward, the engine, must be balancing all that friction holding you back. So it is 100. Because the force of propelling is balancing that of friction in this case. One's positive, one's negative, one's to the right, one's to the left. But if the net force is 0, then those must be equal. Do you see that mathematically? So if it takes 100 newtons to pull something at a constant speed, then I know friction is pulling back with 100 newtons. If you pull with 200 newtons, what happens to its motion? If you make this 200 newtons, it accelerates and to the right. And all you do is this. Instead of that being 0 now, it has some value. You can solve it and find out exactly what it is. We'll cover this again, but for those of you that are getting it. So real quickly, here's one to do at a party trick, and we'll let you go. I cut this out of an oatmeal container. You can use a coin. Set it on top, just to remind you of inertia. And if you hit it fast enough, right, it ought to slide out from underneath it. The support force is now gone. Gravity should pull it down. Its inertia hopefully will keep it from moving horizontally when I try to pull it horizontally, and it can fall right into the glass. So for lack of time, this is what you do. You set it up and you're sitting here like this, and you have your friend do it, and whammo! They miss. So you give them another chance. Go faster! And they're whoosh! They're not paying attention. They hit this, it goes flying and breaks. That's happened. It doesn't matter how fast you go here. What you do is you wind up and you go, wah! And they're all impressed. Then you give them another chance and they're still whacking over here. And then you finally share with them the answer. Instead of going here, slow-mo, you ready? Whoosh. And you grab in here. Because when you hit here, what happens to the ring? Doink. It squishes and provides an upward force. Changes the equilibrium and sure, pops off. But when you grab here, it actually is to your advantage. It squashes. Comes out from underneath it even better. And now inertia can just let it drop straight down. Have a good weekend. Be safe.